Hey friends, if you think back to 2014, filmmaker Christopher Nolan released a cinematic masterpiece, Interstellar. This movie stood out because it portrayed space concepts like wormholes, black holes, and alien worlds with real scientific accuracy. But the scene that blew everyone's mind came near the end of the film, when the protagonist, Cooper, gets pulled into a black hole named Gargantua. As his spacecraft crosses the event horizon, everything around him turns pitch black. There's nothing but emptiness at first. But the deeper he goes, tiny particle-like specks appear, striking his ship and leaving marks behind. Flashes of light and fiery sparks flare up. The spacecraft is damaged, and Cooper has no choice but to eject and continue falling on his own. Then suddenly, he's no longer in ordinary space. He finds himself inside a five-dimensional construct, a tesseract, a place where time becomes a physical dimension. Here, he is somehow able to interact with his daughter's past using gravity. Watching that sequence, many of us must have thought, is any of this even possible? Does a black hole really look like that from the inside? If a human were to fall into one, what would they actually experience? That's exactly what we'll explore in today's video. For most of human history, black holes were just a theoretical idea. It wasn't until the 1900s that scientists began to seriously study them. A black hole is an area in space where gravity becomes so intense that nothing, not even light, can escape. From outside, there is no way to peek into a black hole and know what lies within. They are like invisible traps lurking in the cosmos, gravitational monsters that devour anything crossing their path.
Friends, to understand where the idea of black holes came from, we have to go back about a century. 100 years ago, humanity had no clue that such objects even existed. The concept only emerged after Albert Einstein introduced his groundbreaking ideas about space, time, and gravity. Einstein's work on relativity is divided into two major theories, special relativity and general relativity. In 1905, he presented the special theory of relativity, which explains how motion, especially speeds close to that of light, affects time. Imagine you're traveling in a spacecraft at extremely high speed. For you, time would appear normal, flowing as it always does. But compared to people who stayed back on Earth, time would pass more slowly for you. This effect is called kinematic time dilation, and you only notice the difference when you return and compare clocks. A decade later, in 1915, Einstein expanded his ideas with the general theory of relativity. Here, he showed that gravity also influences the flow of time. The stronger the gravitational field you're in, the slower time passes for you, compared to someone in a weaker gravitational zone. This phenomenon is known as gravitational time dilation. These two principles, time bending due to speed and due to gravity, laid the foundation for our understanding of black holes.
One of the most striking examples of time dilation in pop culture was shown in Interstellar. When Cooper and his crew land on the water-covered planet near Gargantua, just 1 hour on that planet equaled 7 years on Earth. That extreme time warp happens because the planet orbits dangerously close to the black hole, where gravity is unbelievably strong. Einstein explained these effects using the idea of a space-time fabric, like a stretchy sheet on which stars and planets sit. The heavier an object is, the deeper it presses into this fabric. That bending doesn't just pull other objects toward it, it also slows down time itself. Even energy forms like light, heat, and sound don't escape gravity's influence. This led to a fascinating implication. Somewhere in the universe, there could be regions with gravity so intense that even light cannot escape. And since light wouldn't reflect back from such an object, it would appear completely black and invisible to the eye. That's what we now call a black hole. But when Einstein first introduced general relativity in 1915, black holes were just a mathematical possibility, not something he believed actually existed. He accepted that gravity could trap light theoretically, but he didn't think nature would form objects that extreme. Even the phrase black hole didn't exist before he died. There's another fascinating detail in his theory. Gravity itself isn't instant. Its effects spread at the speed of light. For example, if the sun vanished out of existence suddenly, Earth wouldn't feel the loss of its gravity right away. Just as sunlight takes about 8 minutes to reach us, the change in gravity would also reach us with the same delay. After Einstein, mathematicians and physicists began solving his equations more deeply. Researchers like Carl Schwarzschild discovered that the equations allowed for regions where space-time curved infinitely, the theoretical birth of black holes. By the 1960s, the scientific community began accepting that black holes weren't just hypothetical. Observational astronomy hinted that real objects with these extreme properties might actually be lurking in space. The phrase black hole first appeared in print in 1964, but it became widely used only after physicist John Wheeler adopted and popularized it in 1967.
The name black hole might give the impression that there's an empty pit in space, but that's actually misleading. A black hole isn't a hole at all. It's the remains of a massive star that has collapsed under its own gravity. To understand this, think about how stars function. Even our sun is a giant nuclear reactor. Deep inside, hydrogen atoms fuse to form helium through nuclear fusion, releasing an enormous amount of energy in the form of heat and light. This energy generates outward pressure, pushing against the star's own gravity. So throughout a star's lifetime, two forces stay in balance. Gravity pulls everything inward. Fusion pressure pushes outward. This balance, called hydrostatic equilibrium, keeps the star stable and alive. But fusion can't run forever. The star gradually uses up its fuel, starting with hydrogen and later fusing heavier elements. Eventually, the core runs out of usable fuel. When that happens, the outward pressure drops and nothing is left to counter the inward pull of gravity. At that point, the star begins to collapse in on itself. What happens next depends mainly on how massive the star is. Smaller stars, like our sun, will not become black holes. For reference, the sun has an estimated total lifetime of nearly 10 billion years. However, if a star is extremely massive, far larger than the sun, its collapse can be so intense that it compresses all of its mass into an unimaginably small volume of space. That's when a black hole is born. From here, scientists study the stellar life cycle using diagrams and models that track how stars evolve depending on their size.
What happens to a star at the end of its life depends entirely on how massive it was to begin with. If a star is small or medium-sized, like our sun, it first transforms into a red giant after exhausting its fuel. Later, it sheds its outer layers and becomes either a planetary nebula or contracts into a white dwarf. But if the star is much more massive, the story is very different. When a giant star runs out of fuel, it expands into a red supergiant. Eventually, its core collapses and the outer layers explode in a spectacular event known as a supernova. What remains afterward is a dense core. If the leftover core isn't too large, it becomes a neutron star. But if the remaining mass is above a certain threshold, gravity crushes it even further and it becomes a black hole. To give you an idea of how extreme this is, if a star the size of our sun were compressed into a black hole, the resulting object would only be about 50 kilometers in diameter. That's smaller than many cities on Earth. However, our sun will never become a black hole. Why? Because of a groundbreaking discovery by Indian-American astrophysicist Subrahmanyan Chandrasekhar. He calculated the Chandrasekhar limit, the maximum mass a white dwarf can have before collapsing further. That limit is about 1.4 times the mass of the sun. Since our sun is below that threshold, it will eventually turn into a white dwarf, not a black hole. Now, let's talk about the types of black holes scientists have identified. Types of black holes. 1. Stellar black holes. These form from the collapse of massive stars after supernova explosions. They are the most common type. Astronomers estimate that our Milky Way galaxy alone may contain 10 million to 1 billion stellar black holes. 2. Primordial black holes. These are hypothetical black holes that may have formed right after the Big Bang. They could be as tiny as an atom, yet have the mass of a mountain. Their existence is still uncertain and currently falls under theoretical physics. 3. Supermassive black holes. These giants have masses exceeding 1 million suns and are compacted into a region no bigger than our solar system. Scientists now believe that almost every large galaxy has one at its center. At the core of our own Milky Way galaxy lies such a giant, a supermassive black hole known as Sagittarius A star. The black hole shown in Interstellar, Gargantua, was also designed based on the characteristics of a supermassive black hole.
The black hole in Interstellar, named Gargantua, is an example of a supermassive black hole. These are the giants of the universe, with masses millions or even billions of times that of our sun. Some scientists also hypothesize the existence of a fourth type of black hole, called an intermediate mass black hole. As the name suggests, it would be larger than stellar black holes, but smaller than supermassive ones. However, unlike the other types, evidence for these intermediate black holes is still very limited. One thing that often surprises people, whether from interstellar or real astronomical images, is that black holes aren't simply huge black spheres sucking everything around them. Instead, their structure is more dynamic and fascinating. A key feature is the accretion disk, the glowing orange ring you often see surrounding black holes in movies and high-resolution simulations. This disk forms because the gravitational pull of the black hole attracts surrounding gas, dust, and stellar debris. These materials spiral inward, orbiting the black hole at tremendous speeds. The friction and compression from this rapid motion heat the matter to extreme temperatures, turning it into a plasma-like, almost fluid state, radiating energy in the form of light and other electromagnetic waves. This is why black holes are often surrounded by luminous, fiery rings, despite the black hole itself being invisible. The process is similar in principle to how planets orbit the sun, but the gravitational forces near a black hole are so strong that matter moves much faster, sometimes close to the speed of light, creating spectacular energy emissions.
The accretion disk surrounding a black hole is an incredibly energetic place. Particles in the disk can reach temperatures of millions of degrees Celsius. The closer these particles get to the black hole, the faster they orbit due to its intense gravitational pull. At such high speeds, the particles rub against each other and compress, causing them to glow and emit energy, primarily in the form of X-rays. Movies like Interstellar portrayed this disk remarkably well. The only visual liberty they took was the color. In reality, human eyes cannot see X-rays, so we represent them in orange or yellow hues for clarity. If we could see them with X-ray vision, the disk would appear closer to blue-white. In 2019, astronomers captured the first ever photo of a black hole, M87*, and similar color coding was used to illustrate its accretion disk. One fascinating detail in these real images is that one side of the disk appears brighter than the other. This isn't random, it's due to the Doppler beaming effect. Particles moving toward us seem brighter, while those moving away appear dimmer. By studying this, astronomers can determine the rotation direction of the disk. In Interstellar, the accretion disk also shows a visual illusion. It seems to wrap around both the top and bottom of the black hole. This effect occurs because gravity bends light, curving the paths of photons around the black hole. Viewed from above, the disk would look like a simple flat circle. The dramatic warped appearance is only visible from the side. Finally, surrounding the black hole is another intriguing feature called the photon sphere, a boundary where light itself orbits the black hole. If you were close enough, this would appear as a final glowing ring before the event horizon, a truly mind-bending phenomenon.
Around a black hole, gravity is so intense that even light cannot escape. But before light is completely trapped, there is a fascinating region called the photon sphere. Light is made of photons, and in this region, photons can actually orbit the black hole in circular paths. Theoretically, if you were somehow able to survive there, it might even be possible to see the back of your own head, because light itself is traveling in a loop around the black hole, forming a luminous ring. Beyond this area lies the event horizon, the point of no return. Once an object crosses this boundary, the gravitational pull is so extreme that not even light can escape, making everything beyond it completely dark. For a human falling past the event horizon, escape would be impossible. If light cannot break free, there's no way a person could. In Interstellar, Cooper's spacecraft is shown crossing the event horizon and entering a 5-dimensional tesseract. This part of the movie is purely speculative, since no one truly knows what exists inside the event horizon. The filmmakers consulted Nobel Prize-winning physicist Kip Thorne to ensure scientific accuracy wherever possible, but the interior of a black hole remains one of nature's greatest mysteries. According to Einstein's general theory of relativity, the very center of a black hole is called the singularity. This is where the curvature of spacetime becomes infinite. Remember the spacetime fabric mesh we discussed earlier? The heavier an object, the more it warps this mesh. In a black hole, the warping becomes extreme, stretching spacetime to infinity. At the singularity, gravity is so strong that it theoretically slows time down infinitely, affecting everything: energy, matter, and even the flow of time itself. It is the ultimate extreme predicted by the laws of relativity.
But what does it really mean when we say time slows down infinitely near a black hole? Could it be that if someone somehow fell in and managed to escape, assuming that were possible, the universe outside would have aged immensely? The truth is, we don't know. All we have are theories and hypotheses. Some physicists suggest fascinating possibilities. Since light cannot escape a black hole, we cannot see inside it from the outside. One idea is that within the event horizon, light could bounce multiple times before reaching the singularity, meaning there might be some visibility inside, at least theoretically. So far, the only direct evidence we have of black holes comes from a single historic image. On April 10, 2019, the Event Horizon Telescope captured the first ever image of a black hole, providing practical proof of their existence almost 100 years after Einstein's theory suggested them. Of course, if you were to fall into a black hole, the outcome would be fatal. The immense gravitational forces would stretch and tear your body apart in milliseconds, a process sometimes called spaghettification. So yes, it's not survivable. However, there's no need to panic about black holes. Many people imagine them as cosmic vacuum cleaners, sucking up everything and eventually destroying the universe. That's not how it works. Supermassive black holes exist at the centers of galaxies, including our Milky Way. Just like planets orbit the sun in our solar system, stars and other matter orbit around these black holes. The forces are intense, but as long as you maintain a safe distance, you are completely fine. As for the 5-dimensional concepts shown in Interstellar, They remain purely speculative and fascinating ideas. We'll explore those in a future video. That's all for now. If you enjoyed this, check out more videos on space.